Acetaminophen is one of the most heavily consumed pharmaceutical compounds in the world. Stacked in bulk in pharmacies, it's relied upon daily for minor aches. We rely on tamper-proof seals to guarantee safety. However, once inside the body, the biochemistry of this drug exploits a specific vulnerability in our metabolism. Once swallowed, the active compound bypasses the stomach lining. It enters the bloodstream and funnels directly into the hepatic portal vein. This vein carries the compound straight into the hepatic circulation. Its primary destination is the liver. The liver functions as an aggressive, highly reactive chemical processing plant. Under specific conditions, its own machinery converts this benign pill into a chemical threat. The liver must remove environmental toxins and xenobiotics from the blood, but many of these compounds are hydrophobic. They repel water. Because human excretion is water-based, these chemicals cannot simply be flushed out of the system. To solve this, the liver uses a two-tier biomechanical system within a hepatic lobule. Phase 1 is the alteration phase, where enzymes physically change the chemical structure of incoming toxins. Phase 2 attaches specific molecules, making them water-soluble for safe excretion. This elegant architecture is essential for survival. However, these same metabolic steps can generate highly toxic reactive species. Phase 1 detoxification serves as the first line of defense. Every pharmaceutical compound ingested passes through this initial metabolic checkpoint. The heavy lifting is done by Cytochrome P450 enzymes. These robotic arms attach chemical groups to passing molecules to prepare them for the next stage. Chemical alteration does not automatically result in biological neutralization. Phase 1 is a volatility stage. By changing a molecule's structure, CYP450 enzymes can create highly reactive, unstable intermediate compounds. This phase merely primes the chemical for elimination. In the short term, the liver has turned a stable compound into an agitated metabolite. When we introduce acetaminophen into this assembly line, we can observe the system's primary vulnerability. Within the P450 family, the CYP2E1 pathway uniquely interacts with this drug. Through a process called bioactivation, the CYP2E1 enzyme strips the drug into an oxidative, destructive metabolite. This microscopic event occurs across the population millions of times a day. This specific metabolic misfire accounts for over 50% of acute liver failure cases. Toxicity occurs when the liver's own enzymes transform a standard dose of medicine into a molecular threat. Once bioactivated, these volatile red metabolites progress deeper into the cell. Their destination is Phase 2, the conjugation station. This system is designed to neutralize the volatile intermediates generated during Phase 1. Inside the station, the liver attaches molecular tags, specifically glutathione, to the radicals. This converts the volatile compounds into inert droplets. These droplets are now water-soluble, which is necessary for renal and biliary excretion. Hepatic survival depends on Phase 2 catching and neutralizing every metabolite generated by Phase 1. Glutathione, the primary conjugating molecule, is a finite resource. Repeated doses of acetaminophen continuously demand glutathione for safe processing. We can see those reserves draining here. When the glutathione pool is completely exhausted, the conjugation station halts. The bioactivated radicals bypass the station unchecked. Without glutathione to neutralize them, these oxidative metabolites physically attack the surrounding biological infrastructure. This attack leads to rapid hepatocellular necrosis, where cellular machinery is destroyed from the inside out. A clinical overdose represents the mechanical failure of this rate-limiting bottleneck, leaving the liver unprotected against its own metabolites. Plant-derived compounds can intervene in this failing system. Curcumin, a flavonoid, physically binds to the CYP2E1 enzyme and jams the mechanism. This targeted inhibition downregulates the toxic pathway. The creation of destructive metabolites ceases, allowing the liver to function without generating reactive species. By modulating enzymes, we can prevent the bottleneck from being tested. We can proactively silence the biological machinery that creates these toxic intermediates. Finally, the liver requires assistance in replenishing depleted Phase 2 resources. Silymarin, an extract derived from milk thistle, possesses specific properties that shield the liver from this metabolic cascade. Silymarin acts as a structural shield, actively restoring the finite glutathione reserves. When these interventions work together, the system stabilizes. Phase 1 and Phase 2 synchronize to process compounds safely. Hepatic detoxification operates as a quantifiable mechanical sequence governed by precise chemical rules. By mastering the biochemistry of Phase 1 alteration and Phase 2 conjugation, medical professionals can intercept metabolic misfires and address cellular damage before it becomes terminal.